So our next speaker is Nichole Berry, and she's going to talk about chasing the Epoch of Reionization using 21 centimeter power spectrum analysis from the Murchison Widefield Array.
Yes, thank you. So my name is Nichole Berry, and I'm a postdoctoral researcher at the University of Melbourne. And today I want to talk about trying to measure the Epoch of Reionization in a slightly different sense, in a slightly different study than mostly is what is being talked about at this conference. And in particular, I want to look at it with Australian instruments. So I'm sure you've seen this multiple times already, but this is just a summary slide of a variety of different studies that have gone into trying to measure the IgM neutral fraction as a function of redshift. And they range from quasar studies all the way through cosmic microwave background studies. But in general, these studies have two features to them. Sometimes they can be line of sight studies. So in particular for quasars, you're looking at a particular line of sight and how the neutral fraction is in that particular line of sight. Or you can have model dependency. So for example, for the cosmic microwave background tau measurement, that is actually model dependent on a dust mask. And there's been a lot of studies to try to reduce this, but there's still a lot of room for a type of study that is model independent and is more global to help give context to these other studies. And that in particular is the 21 centimeter line of the neutral hydrogen. So this is a simulation of the Epoch of Reionization by the Dragons team, Paul and Simon in particular. And you can see the neutral hydrogen in the red here, and the ionizing sources turning on at about redshift of 15, all the way through about a redshift of 6. And as these ionizing sources ionize the surrounding neutral hydrogen, it dissipates. So if you're looking for the 21 centimeter line, you can actually look at a variety of different frequencies and make a movie of the universe as it's evolving through its last phase change. And you can also probe a lot of cosmological parameters in addition to the astrophysical parameters of the first sources themselves. So this is a GIF of a simulation done by Bradley Gregg and Jae-Hong Park of the types of parameters you can probe using the power spectrum of that 21 centimeter line. So they're just varying 8 different parameters and showing how that changes the absorption and the emission of the 21 centimeter line. And if I take a snapshot of a very typical model universe, on the top panel here, you have the universe slice as a function of frequency for the 21 centimeter line. So by the time the 21 centimeter line gets to Earth, it's in the radio frequencies, about 200 megahertz through to 60. And in the middle panel, you have the brightness temperature of that line relative to the background. And so you have an absorption feature and an emission feature. And on the bottom, you have the power relative to the background. And you can see that there's some fluctuations and a lot of cosmological parameters you can probe just by looking at this one line. And it's at roughly about 10 millikelvin squared. But that's really faint. And so to put this into perspective, I'm going to give an analogy. It's like trying to measure a light bulb on Pluto in the middle of a lit stadium. And this is because not only is the 21 centimeter line very faint, but it's in the radio spectrum. And so all of the radio synchrotron sources between us and the Epoch of Reionization are extremely bright and drown out that signal. But they have a smooth spectrum, whereas the 21 centimeter spectrum is varying as a function of frequency. And so what you can do is you can take a Fourier transform and naturally separate these signals from one another. So on the left here, we have a power spectrum This is the type of plot I'll be showing today. And on the x-axis, you have spatial scales. So left would be larger bubbles, larger imprints, and to the right would be smaller. And the more power you have in a specific K-bin indicates the size distribution of that bubble in the early universe. And there's a whole lot of different instrumentation around the world that's trying to measure this 21 centimeter signal. And in particular, I use the Murchison Widefield Array, or the MWA, in Western Australia. And there's two main systematics that we have to be aware of in trying to make this power spectra. You can group them into analysis or observational systematics. Analysis systematics come from the pipeline, and there's a lot of bells and whistles to pipelines. This is just a very typical pipeline setup with a variety of different modules, if you will. And I want to, in particular, pick out these modules because we make a matched simulation with these modules for every single data analysis that we do. It's completely noiseless and it's full of foregrounds. And what you're looking at with this particular power spectrum is a theoretical EOR signal in brown and the simulation in blue. And so what you want out of your simulation is for it to be lower than the actual EOR signal, because the simulation traces out the systematics that you see. If it were perfect, theoretically, that blue line would be at 0. So you can see with this simulation, which was done in 2016, that we couldn't even theoretically detect the EOR. But over the course of 3 years, we improved our analysis greatly such that we could theoretically detect the EOR, which is definitely a good first step. And I don't have a lot of time to talk about these changes, but the main takeaway from all of them is that you need to have 1 part in 10 to the 5 spectral precision to hit that level of systematics. On the observational side of things, this is looking up at, from the MWA over the course of a few seconds, Mike Walensky found this object, and we don't know what it is. It's not aliens, at least we don't think so. We don't actually know what it is, but given the spectral signature of this signal, it appears to be digital TV channel 6 being reflected off a bottom of a bush plane from Perth, which is a town about 500 miles away. So that just kind of gives you the scale of the RFI mitigation that we need to perform. So this is what the field looked like at the end of 2019. Again, power spectrum, power as a function of K, with a variety of different publications and their redshift shown in color. And I want to point out a particular one. So we took Beardsley 2016 data here in the bow ties, that same exact data set. We re-reduced it with all of our improved analysis systematics. And we also removed as much of that channel 6 as possible. And then you get this solid line for Berry 2019. And that was an improvement of about a factor of 10. And then fast forward to today, 2 more papers came out that are further improving upon that limit. And in particular, I want to point out Mertens 2020, which is a LOFAR paper, a different instrument. They also improved by about a factor of 10. So we're all improving at roughly the same rate. But we're still orders of magnitude away from the EOR signal, as you can see here. However, we're starting to get to a regime where we can rule out certain models of the Epoch of Reionization. In particular, LOFAR and the MWA are very complementary because they're taking data at different redshifts. And so together you can use them to disfavor a wide variety, wide class of models. So they both disfavor cold reionization. They also disfavor soft band X-ray luminosities below about 10 to the 38. And so if you're interested in learning more about these constraints, you can look at Greg et al. 2020 and his upcoming other paper as well. So in summary, the 21 centimeter power spectrum analysis is a global model independent study, which hopefully can give context to all the other EOR studies out there. However, it's difficult because it needs to be extremely spectrally precise and have extremely high RFI mitigation. However, we are starting to roll out some extreme reionization models, and it'll be a good space to pay attention to as we start to lower those limits and rule out other models as well. And so with that, I'll take questions.
Okay, thank you very much, Nichole. So a few quick questions. Anonymous says, what do you think we can ultimately learn before the arrival of full SKA?
For the SKA?
Before, what can we learn before?
Yeah. Right now, what we're attempting to do is just get a measurement of the power spectrum itself. This might just be a one-off measurement using our best frequency band. So that would be a measurement of 1 redshift. So it would kind of just give a benchmark for the SKA, I would say, and that's what we're hoping for at the moment. And of course, with the SKA, we would hope to go even further, maybe even one day image the 21 centimeter signal.
Okay, I had one question myself. So you've just very impressively improved the pipeline with a factor of 10. Still need quite a few. Where's the next sort of factor of 10 coming from? Like if you look at that, all those steps that you outlined, what is the most likely thing to give you another order of magnitude?
Right. So some recent work I've been working on is to avoid taking an FFT at any point because whenever you take an FFT, you get aliasing. Whilst it's quick, it doesn't quite have the precision that we need. And so I've been trying to move towards a model of using Gaussians or other analytic Fourier transforms to do the same things, to give us the same results, but without that aliasing.
Okay. Another question, do MWA and LOFAR constrain the lower limits of the IGM temperature?
Not at this point. And it might be a while before we get to that. Right now, we're just doing extreme models.
Okay. And a question, how will you verify a detection? Cross correlations?
Yeah, that's an extremely difficult question, and one that I've had before. At the moment, it's not necessarily the biggest concern of ours to because we're just so far away from actual detection. But I think that no matter what we do, the only way that you can actually confirm a detection is to detect it once with an instrument and detect it again with a completely different instrument on the other side of the planet.
Okay. And then final question, how do the current constraints compare with original predictions for the experiments? Have you done better, worse than expected so far?
We've done worse. So it's been quite a learning experience, and I think this was really important to do before SKA came around. There were a lot of systematics that were inherent to the measurement itself that we cannot disentangle ourselves from, that we didn't know were there until we looked at the data for the first time and we're like, what is this? For example, there's a chromaticity that gets convolved into your data via the instrument itself, due to the fact that the spacings between your interferometric elements vary as a function of frequency. And that variation as a function of frequency, as soon as you take a Fourier transform, contaminates your signal. And so for the most part, these instruments have been a learning experience. And to be honest, I think a lot of people who first proposed for these instruments thought we would have measured it within a couple of years.